There is hidden beauty in the world that we cannot see. One of them is complex numbers. Complex numbers are not just a calculation tool. Behind them lies an astonishingly beautiful harmony and shapes beyond imagination. In this video, let's dive into the hidden charms of complex numbers together. Quadratic function, y equals x squared minus 1. In this graph, the value of y is 0 when x is 1 or minus 1. Next, let's slightly modify this graph a little and look at the graph of y equals x squared plus 1. In this graph, there is no x for which the value of y is 0. But if we extend the domain of x to the complex plane, we can find the points where the value of y is 0. The fact that x squared plus 1 equals 0 means that x squared is minus 1. A number that, when squared, equals minus 1 is written as I and is called an imaginary number. Milan, Italy. Approximately 480 years ago in 1545, Girolamo Cardano, born in this place, published Ars Magna, which would later become a historic book on algebra. Cardano was known for his achievements across diverse disciplines, excelling as a physician, mathematician, philosopher, and astrologer. Cardano wrote this in chapter 37 of Ars Magna. What are the two numbers that add up to 10 and multiply to 40? For example, if two numbers are both 5, adding them gives 10 and multiplying them gives 25. So what are the numbers that add up to 10 and multiply to 40? Cardano wrote those numbers like this. In modern writing, this would be 5 plus root minus 15 and 5 minus root minus 15. These two numbers indeed add up to 10 and multiply to 40. However, Cardano also wrote that numbers with a negative value inside the square root were useless, of no practical value. In the mathematical framework of 1545, there were no numbers with negative square roots. So Cardano was confused and wrote this. However, numbers in which a negative value appears inside the square root, that is, numbers whose square gives a negative sign, are the important numbers known today as imaginary numbers. After Ars Magna, imaginary numbers spread around the world, and many mathematicians began to explore them. Then, around 1800, the German mathematician Gauss proposed the fundamental theorem of algebra, which states that any equation can be solved by using imaginary and complex numbers. Complex numbers are new numbers that extend beyond the range of real numbers. Complex numbers can be written as a single expression using real numbers a and b and I, the imaginary unit, as z equals a plus bi. The value of the real part is taken along the horizontal axis, while the value of the imaginary part is taken along the vertical axis. This plane, where points are determined by these two values, is called the complex plane. The fundamental theorem of algebra, as demonstrated by Gauss, states that if complex numbers are included, an nth degree equation will always have n solutions. Since x squared plus 1 is a second degree function, according to this theorem, there should be two solutions where this equals 0. Let's check this. First, we replace x with the complex number z. This means expanding the range of inputs for the function from real numbers to complex numbers. When there were only real numbers, there was no point where the graph intersects 0. But what happens when we include complex numbers? In fact, when the function includes complex numbers, the output is also a complex number with both real and imaginary parts. Therefore, it cannot be directly represented on a graph. To visualize this, we will separate the real and imaginary parts and plot them individually. First, we express z as a plus bi, then expand and separate it into real and imaginary parts. Next, we plot the real and imaginary parts on separate graphs. On the left is the graph of the real part, and on the right is the graph of the imaginary part. We also show where the value is 0 with white lines. By overlaying these two white lines, we can see that at the points where the lines intersect, both the real and imaginary parts are 0. In other words, these points are the solutions to the original equation. As you can see, there are exactly 2 points. Now let's look at the solutions to a cubic equation. In the same way, we separate the real and imaginary parts and plot them, resulting in a more complex graph than before. Let's overlay the two graphs. Now the number of solutions is 3. Next, let's take a look at the solutions for 4th and 5th degree equations. The 4th degree equation has 4 intersections, while the 5th degree equation has 5. Now let's line up the graphs for equations from the 2nd to the 5th degree. By including complex numbers, we can visually confirm the fundamental theorem of algebra, that the number of solutions always matches the degree of the equation. Previously, we graphed the output of a function by separating it into its real and imaginary parts. This time, we'll think of the function as a mapping that moves points on the complex plane to other points. We'll refer to the function as a mapping. How do points in the complex plane move under this mapping? We'll use an image made up of many points to observe how it transforms under various mappings. First, let's consider a mapping that adds another complex number to the original one. This results in a translation. Next, we apply a mapping that multiplies the original complex number by a real number. This stretches or compresses the image. Now, let's see what happens when we multiply by an imaginary number. The image rotates. To understand why multiplying by an imaginary number causes rotation, let's calculate how individual points move. First, multiplying 1 by I gives I. Next, multiplying I by I gives -1. Then, multiplying -1 by I gives -I. Finally, multiplying -I by I brings us back to 1. Indeed, we've completed a full rotation. Next, let's take a look at a mapping called inversion. As you can see, the image is dramatically distorted. In an inversion mapping, points near the origin are sent far away, while the origin itself is mapped to a point at infinity. Interestingly, the complex plane can also be viewed as a mapping of a 3-dimensional sphere. Each point on the complex plane corresponds to a point on the surface of the sphere and vice versa. The 4 mappings we've explored earlier can all be represented as movements of this sphere. When the sphere is translated, the image on the complex plane shifts accordingly. If we change the height of the sphere, the image undergoes scaling, stretching, or compressing. Rotating the sphere horizontally corresponds to a rotation of the image on the complex plane. And when the sphere is rotated vertically, the image undergoes inversion. In an inversion, the point at infinity on the complex plane corresponds to the very top of the sphere. Now let's step away from complex numbers for a moment and explore something even more intriguing. The inversion mapping we just observed can be thought of as mapping the 2-dimensional plane onto a 3-dimensional sphere, rotating that sphere in 3-dimensional space and then mapping it back to 2 dimensions. This time, let's raise the dimensionality by 1. We'll map a 3-dimensional object onto a 4-dimensional sphere, rotate the sphere in 4-dimensional space, and then project it back into 3 dimensions. What you're seeing now is a transformation applied to a human-shaped object in 3D space. where the object's fingers are placed near the origin during the mapping process. Now let's place the origin near the object's face. In 3 dimensions, the inversion mapping retains its property of moving points near the origin far away. You can see how parts of the object near the origin are dramatically deformed. Finally, let's place the origin near the center of the object's body. Here's how it transforms. These transformations may look strange and surreal. However, in the 4-dimensional world, they are simply rotations of a sphere. What we are seeing here is merely their shadow. Next, let's explore complex numbers from yet another perspective. On the complex plane, the angle a point makes with the real axis is called the argument. This dartboard-like pattern you see here represents the complex plane, with colors applied periodically based on the distance from the origin and the argument of each point. Right now, we're visualizing the simplest function, fz equals z. The colors are determined by the logarithm of the distance from the origin, which is why the pattern changes more intricately near the center. Now, if we multiply this function by exponential it, where t increases over time, the dartboard pattern rotates. If we modify the exponent to exponential t, the dartboard shrinks toward the center. Next, using exponential t multiply 1 plus I, the pattern rotates and spirals inward, creating a vortex-like motion. The exponent of the exponential function determines the rotation, shrinking, and spiraling behavior. Now, let's apply the same transformations to the function fz equals 1 over z. Do you notice a difference between the motion in the top and bottom rows? In the top row, the pattern rotates and is drawn into the origin, while in the bottom row, the pattern rotates but appears to emerge from the origin. This difference arises because for the top function fz equals z, the function's value at the origin is 0, whereas for the bottom function fz equals 1 over z, the value at the origin is infinite. Here, we'll refer to points where a function becomes infinite as pole, and points where the function equals 0 as 0. Poles correspond to where the denominator of the function becomes 0, and 0 corresponds to where the numerator becomes 0. By carefully designing a function, we can place poles and zeros anywhere on the complex plane. Let's observe how the patterns and motions change depending on the arrangement of poles and zeros. First, let's place 1 pole and 1 zero side by side. This creates the following animation. To make the motion clearer, let's apply a blur effect to the animation. When the exponent is it, the flow forms loops around the pole and 0. When the exponent is t or t times 1 plus I, we can observe a flow emerging from the pole and being drawn into the 0. Next, let's arrange 2 poles and 2 zeros in a crossed pattern. Here, the flow emerges from the 2 poles and converges into the 2 zeros. Now let's place 5 poles and 5 zeros alternately in a circular pattern. By coloring the animation based on the argument of each point, we get this beautiful result. Let's explore the fascinating property behind this pattern. This diagram represents the argument as the direction of arrows. Now let's draw a closed curve around these arrows and observe how their directions change as the curve moves along. First, let's draw a closed curve that encloses a 0. The arrows along the curve rotate counterclockwise, completing 1 full turn. Next, let's enclose a pole. This time, the arrows rotate in the opposite direction, completing a full clockwise turn. In fact, the number of times the arrows rotate is given by the number of zeros inside the closed curve minus the number of poles, with counterclockwise as the positive direction. This is known as the argument principle. For example, let's enclose 3 zeros and 1 pole within the curve. According to the argument principle, the rotation count should be 3 minus 1 equals 2. Indeed, the arrows complete 2 full counterclockwise rotations. The argument principle holds true regardless of the shape of the closed curve. Even if we draw a complex curve like this one, as long as it encloses the same 3 zeros and 1 pole, the rotation count will always be 2. Next, let's enclose 2 zeros and 2 poles. In this case, 2 minus 2 equals 0, so there is no net rotation. Now, let's enclose 5 poles. As the argument principle predicts, the arrows rotate 5 times in the opposite direction. It's fascinating how the change in argument is connected to the number of zeros and poles. This very property is what creates the intricate patterns we've been observing. Now, let's explore the exponential term exponential it that has been central to these animations. What exactly is this number? To understand it, we'll start by looking at how exponential ix can be expressed as an infinite sum. This type of expression is called a series. Similarly, the sine and cosine functions can also be represented as series. If we compare the series for exponential ix with those for sine and cosine, we can see that the terms of exponential ix include both the series for cosine and sine. This means that exponential ix is equal to cosine x plus I sine x. On the complex plane, taking the real axis as cosine x and the imaginary axis as sine x, increasing x causes exponential ix to trace out a circle. This circular motion is the fundamental source of the rotations we've observed in the patterns. Now, let's substitute x equals pi into exponential ix. Since cosine pi equals minus 1 and sine pi equals 0, we find that exponential I pi plus 1 equals 0. This equation is known as Euler's identity. The Nobel Prize-winning physicist Richard Feynman once called it the most beautiful equation in mathematics. One reason this equation is admired is that it connects 5 fundamental numbers: the Napier number, the imaginary number, the circle ratio, the multiplicative identity, and the additive identity. The multiplicative identity is the number that leaves any value unchanged when multiplied, and the additive identity is the number that leaves any value unchanged when added. Both have special significance in mathematics. The elegance of this equation lies in how it unites these 5 important numbers in a single, concise formula. Many find profound beauty in this simplicity and interconnectedness. The Mandelbrot set is one of the most well-known shapes created by complex numbers. Here we'll introduce a variation called the Buddhabrot. The Mandelbrot set is generated using this formula. In this formula, once the initial value c is chosen, the subsequent values are determined iteratively. Substituting a complex number for c corresponds to moving a point repeatedly on the complex plane according to this formula. Let's observe the motion of a point based on its initial value c. For one starting point, the motion settles into a repetitive cycle after several steps. Next, let's choose a different value for c. This time, the point escapes off the screen after a few iterations. Now, let's analyze the behavior of a grid of points, each with a different initial value of c. The motion of these points falls into three categories: divergence, points that eventually escape to infinity; convergence, points that settle into a single location; oscillation, points that repeatedly move between a finite set of positions. Through repeated iterations, the set of points that do not diverge forms the Mandelbrot set. The Mandelbrot, on the other hand, is based on the trajectories of the points that do diverge. Specifically, it visualizes the paths these points take before escaping. Let's look at a Mandelbrot image based on a fixed number of iterations. This image was created by calculating the motion of 24 million points and plotting the paths of those that diverged within the given number of iterations. The brighter areas indicate regions where more points pass through. As we increase the number of iterations, the Mandelbrot becomes increasingly intricate and detailed. The name Mandelbrot comes from the resemblance of its intricate patterns, when highly refined, to the figure of the Buddha. This stunning complexity arises from points that take longer to escape, leaving behind these beautifully intricate trajectories. Let's take a closer look at the movement of this point. It neither converges nor oscillates, but instead moves erratically across different regions. After 2,167 steps, it finally diverged. The trajectory it followed before diverging creates a fascinating pattern. This motion contributes to the intricate structure of the Mandelbrot. While this point took 2,167 steps to diverge, some points take much longer to do so. What happens if we include points that take even longer to diverge and plot a massive number of them? This image was created by setting the maximum number of iterations to 100 million and plotting the trajectories to 100 million points. The colors represent the number of iterations required for divergence. The result resembles a photograph of a cosmic nebula. With increased iterations, loop-like patterns similar to those we observed earlier emerge throughout the structure. The study of the behavior of complex numbers under iterative formulas is known as complex dynamics, a field that has captivated many mathematicians. The Mandelbrot is based on the Mandelbrot set, which was introduced in 1980 by mathematician Benoit Mandelbrot. As a researcher at IBM, Mandelbrot used the computing technology of the time to generate this visualization of the Mandelbrot set. It's quite simple compared to what we see today. Creating detailed images like the ones we've seen requires immense computational power. However, compared to 1980, modern computers are exponentially more powerful. With a basic understanding of programming and mathematics, it's now possible to create such images on an ordinary computer. In this video, we explored complex and imaginary numbers in various ways. Imaginary and complex numbers are used in numerous fields, such as electrical engineering, cybersecurity, and computer graphics. They also play a crucial role in modern physics, particularly in quantum mechanics, where the Schrödinger equation, one of its fundamental equations, contains imaginary numbers. In fact, quantum mechanics would not exist without them. Complex numbers are mathematical constructs developed by mathematicians. Although we rarely think about them, they are deeply connected to many phenomena around us. In this episode of Visualium, we have admired the beauty of complex numbers. Next time, let's explore new vistas together.